Welcome back, friends. We are in the final stages of our course on quantum mechanics in the relativistic regime, and I am sure many of you have already have some idea about the entire course we have been dealing with essentially, and you may have some questions about this course because you may be thinking why do we need this course, because there are these modern approaches to quantum field theory and which of course how hopefully I will give in the next lectures on modern approaches. And why do you need this these kind of techniques and everything? Okay, they do calculate tree level process and you can do renormalization and everything in this methodology also, but why do you need this kind of things in which you do take Dirac fermionic fields as completely as as wave functions, whereas sometimes you are treating the photon field as a dynamical field, you second quantizing the photon field, which we also did not do completely because it is an involved process, but it will take several more hour lectures because in a 30-hour lecture course it may not be able to finish it. But anyway, you got the gist that you are quantizing the electromagnetic field, but you are not quantizing the Dirac field and you are still working out and everything. And why is this hodgepodge approach and what is this entire thing? Why do you still need to learn it in 2025? This these methodologies essentially, when you know the quantum field theory is in full force and it can you will be used to calculate everything. I hope I will convince you today that there are still some problems which we cannot address in full quantum field theory. Okay. There are these problems which you cannot completely address in quantum field theory, and the methods which you learnt in this course are the best methods which you have essentially. Okay. At least the state of art methods, these are still the state of art methods which are just almost 80-90 years old methods essentially, I should say 60-70 years old methods, and but these methods are the best methods still we have in the market to deal with the problems which I am going to tell you about essentially today, and this I hope will convince you that taking this course was a very important thing essentially, that this course was useful essentially. One of the things okay, just to recap what we have covered in this course, we have covered various aspects about calculating Feynman diagrams. We made a one-to-one corresponding starting with Green's functions to Feynman diagrams, and then we started calculating the simple QED process, and so we did Compton scattering, Babar scattering, Molar scattering, pair annihilation and pair creation. These 5 are sort of your fundamental QED process whose tree level calculations you do not need full quantum field theory, you can calculate just by multiplying using the Feynman rules which we derived using the Green's functions essentially. Okay. To do this you do not need full field theory, okay, you just use the Green's functions methods and then you use this Feynman rules and that is it, you get your calculations, you have the differential cross sections and everything. Now we also and around, but when we have to treat the photon field as dynamical, you have to quantize it, you have to quantize it in terms of some polarization vectors and some plane waves, which you have to do it anyway. So you have to quantize the photon field in certain cases, but in other cases what happens is the photon field, even if you take it to be non-dynamical, you just take it to be a static photon field, as we have seen, if you even if you take as a static photon field, this the Green's functions methods are applicable because the Fourier component of 1 by r potential is nothing but 1 by p square, essentially 1 by p square, which is exactly the propagator of the photon. Good. And then putting this back into this and then using for the Dirac wave functions, you use the various trace formula which we have covered. Essentially we have covered all these trace theorems, and then you end up having your matrix element, and taking the square of the matrix elements or the mod square of the matrix elements, we have seen that you can get the differential cross sections. And when you are taking the mod square, if there are two diagrams, you have to take the interference terms also into the consideration, which also we had taken into which also we covered essentially. Then we move to other interactions other than other interactions which are like scalar interactions, and we started with the Ikawa potential, and the Ikawa potential I showed that it is equivalent to if you put in a Ikawa potential, where is it, if you put in a Ikawa potential, it is in the equivalent to a mediator with respect to q square minus mu square plus m square, which is nothing but the Klein-Gordon propagator. These are extremely relevant physics points, essentially these are extremely relevant physics points which are useful nowadays, even now essentially. Okay, these are useful. We learned from quantum field theory point of view that you take it in terms of as you will see in the next series, I hope, which I want to do essentially. You will see it as a time order product of correlation functions, and these correlation functions are now expanded in terms of Fourier modes and raising and lowering operators, and then this you use the canonical equal time commutation relations, and that is how you derive your propagator. But deriving this in terms of the Green's functions methods are also very physically intuitive, and they can be applicable to the systems which we will be talking about, which have no way of dealing them, at least in a concrete sense, in quantum field theory essentially. Okay. So the quantum field theory, okay. So then we use the Ikawa propagator, which is nothing but a scalar function, and then we talked about the infinities which come into higher and higher dimension while doing with higher and higher order in perturbation theory. We computed the higher order perturbation theories, and then we showed that there are these infinities which has to be removed by the process of regularization and renormalization. And finally what we see is that the renormalization has a physical effect, essentially that whereas the physical, when we say the physical mass is, which is something which is the pole of the propagator, which does not change, but the renormalized mass changes with energy. Similarly the coupling, which is defined at q square is equal to 0, does not change, it is defined at q square is equal to 0, but the moment q square goes to any other value, the coupling also changes. So this is because as you increase the probe photon to detect a test electron essentially, so you keep producing larger number of positron electron pairs, electron positron pairs, which are all virtual, which will modify your which will sort of screen your charge essentially, which will sort of screen your charge, and your bare charge, which is infinite, like in what happens in classical electrodynamics also, the bare charge is infinite. As you increase the photon thing, you start going closer and closer, you remove this cloud, go closer and closer to the original charge, and you see an increase in the effect of the total charge essentially. Very good. Okay. And there are, okay, I will just say in words, because this will be covered more in quantum field theory 1, and okay, I will just say more in words that to show an all order polarized renormalization, the QED theory which we encountered essentially, I will just make this statement, the QED theory is renormalizable at all orders in perturbation theory, and that is the reason why you can make more and more higher and higher precise calculations in this particular theory. Now the present precise calculations go up to 4th order in perturbation theory, and and they require a lot of new techniques essentially. So new mathematical techniques, new computational techniques, and so on. So and the QED theory is renormizable at all orders in perturbation theory, which is an important result actually. This is an very important result to make it attach so that you can make connections to experiments. So the renormizability, which means that you remove the unphysical quantities in your theory, which you remove the unphysical infinities which come here in your theory, and make proper predictions, is a very important quality of a quantum field theory essentially. Okay, it is a very important. Such quantum field theories can make physical observers. Okay, good. Now one of the most important predictions of this entire Dirac theory is so called the G-2 of the electron. The G-2 is nothing but the gyromagnetic ratio or magnetic moment. So if you put the electron inside a spin, inside a magnetic field, essentially it has a dipole moment, and that dipole moment, okay, because of the spin, arises due to the spin of the electron. And like I said, Dirac particle describes spin half particles. So the dipole moment corresponds to the spin half particles, okay, of the electron, and so this G-2, okay, the dipole moment, so the gyromagnetic ratio is equal to 2. Okay, it is equal to 2 because it tells you that the particle has a spin 2. It has a dipole moment correspond to a spin half particle essentially. So this G-2 is, what is this G-2? So the magnetic moment essentially is the dipole moment of a particle inside a magnetic field essentially. If you put the Dirac equation in a magnetic field, so we already did it several times, essentially it tells you that, and if you do a non-relativistic reduction, which we were going to do today essentially, which we do a non-relativistic reduction, it will give you which will give you essentially which will give you the gyromagnetic ratio correspond to a spin half particle essentially. It gives this 2 actually, but this gyromagnetic ratio has loop corrections like this. Okay, this is first order, this is second order, and so on. So the gyromagnetic ratio has higher order corrections in perturbation theory. So these higher order corrections in perturbation theory, so will deviate G is equal to 2 ratio. G is equal to 2 is no longer 2 when, so this is gyromagnetic ratio, G is equal to 2. This is a prediction from Dirac theory. Okay, but once you take higher order corrections in QED, essentially the gyromagnetic ratio will deviate from 2 by some epsilon or some delta or something when higher order corrections are there. So G is not equal to 2 when, so G when NLO effects, next to leading order effects are considered essentially. So, to calculate, to test the theory, which is QED, we compute G minus 2 of the electron, compute in theory, okay, and G minus 2 of the electron in experiment. So, you want to change, this is called delta A E, okay. It is G minus 2 electron theory minus G minus 2 electron experiment essentially. This is one of the most important test of quantum field theory of QED essentially, of the one of the most important. So, the G minus 2 of the electron of the theory and everything, and this now matches the theory and experiment matches up to 10 power minus 10 decimals, and the theory is computed up to 4th order in perturbation theory. Fourth order in perturbation theory up to order 10 power minus 10 essentially. See, imagine the precision. So, imagine the precision, that means you can calculate 4th order perturbation theory for the G minus 2 of the electron essentially, and this is amazing precision that required something like about 50 years of work. Because you need to develop new techniques, you need to develop new computational techniques, you need to develop new calculations, because the number of Feynman diagrams you are dealing with are about tens and thousands and millions of these Feynman diagrams, and they all have to be computed essentially, they all have to be computed. Okay. So, this is an important theory thing essentially, that you test your theory very well with experiment and the higher order corrections work. This is a thing which tells you the theory is renounceable, and the renounceability is a very important property, and you can make connections with higher order corrections with the experiments which are also equally precise essentially. You make this high precise corrections and calculations essentially. Well, this is all done, okay. Right now I am talking about things which can be done in quantum field theory, either using Green's functions techniques, which is much more complicated, but using Feynman diagram techniques, just using Feynman diagram. Well, how you get your Feynman diagrams, either from Green's function methods or from quantum field theory in the using canonical quantization or path integral quantization, which will be covered in QFT1, is your problem, but this perturbation technique can be done using you have to use renormalization and everything using Feynman diagrams. But like I said, there are problems which are still cannot be addressed in full quantum field theory essentially, which require the methods which we have been talking about all this while essentially. These methods go in the direction of bound states. These are bound states. So, imagine that, okay, how do you so the X matrix, how do you detect this? There are these bound states which are standard bound states essentially, which are like so the in quantum mechanics bound states are normal. You always have bound states because you have a particle in a well, you have a particle hydrogen atom. The same time in quantum mechanics normal, in the sense that we treat them normally essentially. They are ubiquitous, let me call it, not normal, they are pretty ubiquitous, meaning ubiquitous. okay, they are ubiquitous, they are always there. Essentially you have hydrogen atom, example hydrogen atom. So which is a well known bound state, and there are other bound states also. You have a bound state in delta function, anything which has an energy level negative, okay, in quantum mechanics bounded by some potential, say potential a well or a well or a delta function, negative delta function, anything will also have well, negative delta function, etc., are all bound states essentially. This is in non-relativistic quantum mechanics, this is in non-relativistic. How do bound state appears? In relativistic QM or in relativistic regime essentially. How do you define bound states, meaning what are the process? In quantum mechanics is very standard, you look at the spectrum of the theory and you say all the negative energies states are essentially bound states essentially, okay. You say that negative spectrum of the theory. Now let us look at a simple process, okay. So the bound states always appear, okay, when the S matrix in all orders of perturbation theory is always finite, then there are no bound states. In perturbation series, is finite at all orders, the bound states do not exist. But there exist some cases when the S matrix elements diverges, and this divergence means formation of bound states. This divergence means formation of bound states essentially, okay. This divergence, I mean X matrix series is divergent, I mean it is the formation of bound. Now you may have a better idea if I give you an example. Let us take the simplest example what we have seen in the previous lectures and everything. It is, say for example, E plus E minus going to E plus E minus, scattering part, let us forget, okay. So this Baba's scattering, take only the scattering diagram, let us not let us forget for the present of the annihilation diagram essentially. So it has two diagrams, right, this Baba's scattering has two diagrams. Now the next order in perturbation theory, this is the tree level diagram or the leading order. The next order in perturbation theory okay. And then you also have this diagram and so on. So now let us do some sort of something called a power counting essentially. So power counting, what does this mean, that how does this series diverge? I want to see how does this. So here the momentum exchange essentially will be, or the Q essentially, mod of the Q is roughly alpha times me, alpha times me. And in this case, this gives Q0 is called Q square by 2 me. So this can be written as 1 by 2 alpha square me. So in the higher order in perturbation theory, this goes as 1 by 2. The energy, roughly the energy is essentially has, these are soft terms, essentially soft photons, where the energy of the photon or the momentum of the photon is very similar to say alpha times me. Okay, alpha times me is the soft photon limit essentially. These are photons which are very soft, meaning when I say soft means they are very low energy essentially, they are very low energy. You can always have such an exchange of these photons essentially. So you can have always. So at the end of the day you can have series of these soft photons being exchanged, several of them essentially, where the momentum of the photon is much smaller than the mass of the electron. Alpha is a very small number, it is 10 power minus 2, okay. Alpha is a very small number and the energy of the photon is just p square by m essentially, okay, essentially p square by m. Pc in this case, because the momentum itself is E essentially, so that is what it is. And so this means that this is nothing but the energy is also much smaller than the mass of the electron, the energy of the photon is also much better. So if you look at the series, the total when you sum over all these soft masses series, essentially alpha by q square goes as 1 by alpha plus 1 by alpha 1 by alpha. So you are adding 1 by alpha, take 1 by alpha everywhere, essentially you are adding 1 by alpha, this is 1 by alpha at one point, it gives me 1 by alpha, and if it goes further you are adding 1 more 1 by alpha, essentially you are adding alpha 1 by alpha times alpha square, alpha cube and so on, so essentially. Okay. So this is a series which never converges. This series never converges. It is a divergent series. So you have a 1 by alpha sitting in every term essentially, okay. And this diagram, okay, can imagine a series of ladder diagrams in which several soft photons are being exchanged essentially, okay. And you can see that a part of the thing, okay. Now in this case, this diagram, only the diagrams which are like a ladder, those diagrams diverge, rest of them are convergent in the series. The series of the ladder diagrams you can show it essentially okay. It can be shown that an exchange of a photon, soft photon, in ladder diagrams, these kind of diagrams are called ladder diagrams, gives 1 by alpha, and you keep each of these ladder diagrams gives you a 1 by alpha, and this is not 1 by alpha square, it is not alpha square, alpha cube, alpha, and so that kind of a series. Instead this is a series of the type 1 by alpha times 1 by alpha times 1 by alpha. Such a series diverges. So only the series from ladder diagrams diverges. I am giving you one example, but there are several other examples, and to evaluate these diagrams you need to use something called a Bethe-Salpeter equations, which are very hard to solve, or the other way they are equivalent to some other set, they are roughly equivalent to another set of equations called Dyson-Schwinger equations. Most of the time these equations are very hard to solve, and this gives you, this means the existence of a bound state. Okay, this tells you it gives you the wave function of a bound state in the most relativistic fashion you can imagine essentially. This gives you, okay, the wave function of the bound state if you want. To be more technical, the sum of the ladder diagrams has a pole at the mass of the bound state. So bound state has been observed as poles of S matrix elements, essentially amplitudes and everything, they are poles of S matrix elements. And now, so they are poles of the S matrix elements or amplitudes, and bound states in the real axis these are stable. Bound states on imaginary axis unstable. Or let me say they are below the real axis. Okay, they are in the imaginary plane, essentially these are, more technically I should make it as, they may not be on the axis essentially. So you can have a series of these bound states in the S matrix elements, and some of them, these are all resonances, these are all resonances, these appear as poles, okay, resonances. Resonances are bound states, essentially resonances are, this is how you treat bound states in quantum field theory, essentially this is how you treat bound states in quantum field theory. which is very difficult, okay, which is very difficult essentially, which is extremely difficult to many, because these equations cannot be solved. You can write formally these equations, okay, you can write the Bethe-Salpeter equations, you can write the Dyson-Schwinger equations, but then you cannot solve them. Typically people solve them numerically, okay, sometimes essentially. So you can never solve them, you do not have nice expressions or anything, okay. This is the formal approach for the bound states, these are bound states in, okay. But many of the times, okay, you have, so you can, the bound states are always appearing as some sort of divergences or poles of the S matrix essentially. The poles of the S matrix are your bound states. Now I gave you one particular feature, that there are these soft photons being exchanged, but you can think of soft gluons also being exchanged, you can millions of soft gluons being exchanged forming bound states and everything, okay. You can think in this particular, this is some sort of a naive description of how bound states appears in a typical scattering process in an S matrix picture essentially. This is still a naive picture, but in general, if the S matrix can have poles in the matrix element, and that would appear as a bound state essentially. So this is like a nice geometrical picture in which I drew in terms of all the ladder diagrams essentially. So but it could be more complicated than that essentially, it could be more complicated than that. Now how do you treat this? You treat this by in some cases, for example, this we know that this is in some cases you can solve this by mapping into Schrodinger equation. So in some simple cases, okay, in certain simple cases, if we cannot solve this Bethe-Salpeter and Dyson-Schwinger equations, you can map this entire problem, but simple cases, okay, not for say QCD or something, but in some simple cases you can map this into a non-relativistic system, okay. You can map this into a non-relativistic system of a Schrodinger equation with the potential. You can map this entire thing into a non-relativistic system into a Schrodinger equation. So bound states are still treated in a non-relativistic fashion essentially. The bound states are treated in a non-relativistic contribution, and then there is always this 1 by E ME expansion. Say for example, there are bound states which are made up of electron positron, which are called positronium essentially, and then there are this bunch of excited states called quarkonium essentially. So in the diagrams which I have shown you essentially, so positronium is exactly like hydrogen atom. So you have E plus E minus is exactly like hydrogen atom. So this is called a positronium, where you have an electron revolving around a positron, essentially, but with the reduced mass equivalent to the electron mass essentially. So and then positronium spectrum with QED corrections is studied in great detail. Okay. I would suggest QED and this nice book Landau and Lifshitz QED. It is actually 3 people, Landau, Lifshitz and Petrovsky. Okay, this was published after the passing away of Landau. This has a lot of interesting results about QED, and also another book called Griffith's Introduction. So what we learned this entire thing is there is this concept of bound states, okay, and these bound states have to be treated like hydrogen atom, and then you do the corrections of them from relativistic effects essentially. So that is the way you do it. You do, say for example, any other force, not just QED essentially. You can think in terms of hydrogen, meaning everything you have to map it to a Schrodinger equation or some non-relativistic reduction, and then study the bound states in a quantum mechanical way and study the relativistic effects on it essentially, and study the relativistic effects on it. Okay. So I hope I conveyed you the importance of these lectures essentially, that it is important that these lectures are extremely important to study bound states. These are the techniques in field theory are not so well developed. So these lectures tell you the techniques which are relevant. I may not go into the full mathematical detail, but they will help you to go about working out the details essentially, and we will see certain details in the coming one or two lectures, how to go about this process essentially. Okay, I will stop here and I will continue in the next lecture.